See when we're gonna go live. Are we ready? All right, hello world, it's Siraj, and welcome to this live stream. I'm so excited to see everybody here. What I'm gonna be doing in this live stream is I'm going to be solving this Kaggle challenge. It's called the Invasive Species Monitoring Challenge. There's a lot of plants that are possibly going to destroy the ecology of this area, and what we can do is we can identify those images with those invasive plants. And the way I'm going to do this is using PyTorch. Okay, so PyTorch is, shout out to all the PyTorch lovers in the house right now. PyTorch is a neural network library, and it was invented by Facebook's AI research lab. And it's been gaining a lot of traction, especially in the research community. Now, TensorFlow is the leading, neural network deep learning library out there, and most people use TensorFlow. However, when it comes to research, I'm seeing a lot of PyTorch happening. And in this video, I'm going to describe some of the unique features of PyTorch. We're going to code some PyTorch. We're going to solve this challenge. We're going to learn about ResNets, residual networks, which is a type of neural network that has this really cool idea of skip connections. So I'm going to talk about that. There's an identity mapping. There's some math. There's a little bit of everything. You guys know what the deal is. Okay, so let's get started with this. Thank you everybody for coming here today. I've got a little, PyTorch is amazing, right? All right, so here we go. So PyTorch versus TensorFlow, right? I've got this little graph of like research use cases versus production, Google versus Facebook. But let's talk about some of the unique features, right? So we're going to just compare it with TensorFlow just because TensorFlow is the most used in terms of developer activity on GitHub library out there. If we look at the documentation, I think TensorFlow clearly wins here. I mean, the TensorFlow documentation is massive because A, it's been around so long, B, they're really putting an effort into it. And when I say documentation, I'm not just talking about the API docs on the website. I'm talking about GitHub. I'm talking about number of examples. I'm talking about video content. I'm talking about a lot of different documentation, whether it's on YouTube, whatever. TensorFlow clearly wins. Whereas if you go to the PyTorch documentation, as I am right now, let's make me a little smaller on the corner so we can see this documentation.
Yep, you're small.
If we look at the PyTorch documentation, if you look at any of the functions, well, these are like guides, but let's look at some of the functions like autograd, for example. They're usually just a single page for a function, whereas I feel like there should be more here. But yeah, I think TensorFlow wins in terms of documentation. But where PyTorch wins is when it comes to the graph itself, the computation graph. So this is an image of a neural network that was built in TensorFlow that we're visualizing in TensorBoard, which is the visualization tool. And if you think about it, neural networks are computation graphs. They're just chains of operations applied to variables, and it's just a chain of that over and over and over again, right? Whether it's a dot product operation, whether it's an identity mapping, whatever it is, you have a variable, apply an operation, and just keep doing that until you get an output. So there's a difference here, right? So what PyTorch does, and this is what I believe is really the key feature of PyTorch, what really sets it out from the competitors here or the other libraries, is the fact that you can create a dynamic graph. So a graph is created at runtime dynamically. So just like this, as you're seeing in this GIF here, at runtime, the graph is built. Whereas with TensorFlow, it's a static computation graph. Okay, so at runtime, the graph already was compiled at compile time, and now it's just static right there. So why did TensorFlow do this? Well, first of all, for production use cases, it's very valuable to have a static computation graph. And there are speed reasons for that. There's distributed training reasons for that. But a lot of the newer neural network architectures in research, especially any of the recurrent models, right, where there's this recursion happening, it's better to have that graph be allocated dynamically at runtime. So the graph is built as it's being run. And the reason for this is because a lot of times new operations are applied that wouldn't be applied before. So that's the whole idea behind a dynamic graph, right? You can make changes to it. There's no staticity. What's like the noun for static? Well, adjective, anyway. It's more static. And so when it comes to these newer recurrent architectures with attention mechanisms, with LSTM networks, GRU networks, and now with the new one, which I have an amazing video coming out on, by the way, Nalu, which Trask released a paper on. I know you guys are waiting for that. I've been waiting for that, but don't worry, it's coming on Sunday. It's a sick video. I have so many videos coming out this weekend. You have no idea. OpenAI 5, it's gonna be, literally social media will light up when these videos come out, by the way. Now, back to this. The computation graph is different. You have a static versus dynamic graph. So PyTorch wins in this case. However, I want to note that, Nalu, exactly. I want to note that TensorFlow did like kind of tack this on later with the imperative graph, and that works too. So there is a way. However, it's not native in the way that it was with PyTorch. For visualizations, TensorBoard clearly wins. PyTorch has got nothing, at least from the PyTorch team. I don't know about any like random rogue hacker on GitHub who created some Viz library, but TensorBoard is king here. TensorFlow wins. For debugging, okay, PyTorch wins. Okay, PyTorch wins for debugging because there's a TF debugger called TFDBG, but a lot of people, there's a lot of GitHub issues about it not working, about it not properly documenting things that are going wrong, whereas people just tend to generally love PyTorch's built-in debugger. So PyTorch wins there, right? So rather than like, just saying print, you can actually use these, set trace functions that say PDB has, which is beautiful. It gives you a very detailed stack trace about what you need. And lastly, interoperability, right? So sometimes we can't just do everything natively in those languages. We have to switch to C++ or CUDA, and we need a language that can talk to those in a very easy to use way. And in terms of interoperability, I think PyTorch wins here because it's all about writing interface code that among the different versions of CPUs and GPUs, and as you can see here, it's very easy to have an interoperable graph. Okay, so those are just some of the features that I wanted to talk about. And now, before I actually so guys, I want to say I'm not the Messiah, by the way, because I have been watching Wild Wild Country on Netflix, and I don't want to be that guy. I am not a god. I'm one of you. I'm a developer, and don't worship me as a god, okay? Because that's not what we're doing here. I am just another developer, and we don't want that to be the case, okay? So anyway, let's code out some PyTorch. If you want to call me a god, that's fine though. No, I'm just kidding. Anyway, so let's just code out some simple PyTorch here. So all we have to do is say import torch, and we have some PyTorch going on. See, I just compiled that. Okay, so now what I want to do is I want to build a simple neural network so we could just see like how this works. Okay, so I'm going to do this really quickly. I'm going to hack out a script here using PyTorch, and once we do that, then we're going to have our neural net. Okay, so simple two-layer network. Okay, so far the torch class has a module, and I'm going to show you exactly what that module is going to let us do. We can build a linear layer very easily. Right. Exactly, yeah. You guys are hilarious. Okay, so right, we've got to have the super function, as in any like initialization. We've got to have our super function. And once we have our super function to initialize our constructor, we can say, now after I build this, we're going to start looking at we're going to do some exploratory data analysis. But I first want to just write out this script so we have something there for us. Okay, so in my initialization script, I'm going to be using the input. I'm going to have a hidden state, and I'm going to have an output, right? So d in, h, and d out. That's my input, the hidden state, and my output. And once I have that, now I can create this super function. And so inside of this, I'll have my first linear layer. So Torch's neural net module allows us to create linear layers just like this. Now the input to the linear layer is going to be the input data, and then its output is going to be the hidden state. Okay, and I see that some people say that I have a battery issue. Well, now the battery issue is gone. All right, so back to this. So for our linear layer, and we want to make sure the code is very readable. So what I'm going to do is I'm going to put it right here, and I hope it's very readable to you. Okay. I hope. If you can zoom in a little bit. Let me see how much I can zoom in. I can't really. Please zoom into the code. All right. Let's see. You know what? Let's just script this out in like Sublime or something, so you guys can really see what that's some Nalu code. Don't look at Nalu, guys. I was just making this. Totally look at this sick code, by the way. I was anyway. Where were we? Right, so let me make this bigger, and let me make it in Python, and then we're good. We're good to go. So that way, because sometimes with, you know, these like, okay, no, I'll just call it torch.py. Put it right on the desktop. Boom. Torched. Okay. So torched by Board-Jan LeCun on Twitter. Okay. So now we have the hidden state, and now we're going to have the output, right? So the input to the new hidden state is the input to the next layer is going to be the output from the previous layer. We know that. Okay. So very simple stuff. Now, what else do we need? We need a forward method. So for some reason, PyTorch code usually names their forward propagation method as forward instead of just like build model. Usually this function is called build model, but a lot of PyTorch code uses forward. And I think the reason for that is because forward propagation is dynamic, it's happening at runtime. So people who are writing PyTorch code want to be very specific about what they are doing. And to be specific and to be real, it is better to call, you know, whatever. It's better to call it forward because that's what it is. Okay, so I've got the forward code. Now I need to have my, so I need a batch size. So that's n. N is batch size. I'm going to have our input, my hidden state, and my output. And then it's going to be called 64, 1110. So these are going to be my names for my batch size. So now I can create some random tensors. So the great thing about Torch is it's kind of like NumPy is built into Torch. So we don't actually have to use NumPy. NumPy is like basically built into Torch. So any kind of like matrix multiplication that we want to do, it's all happening inside of PyTorch. Okay. And let me just see what else people are going here. Jupyter's fun, cool zooming. Yeah, great. Much love to everybody as well, of course. Of course. By the way, Dean applications. We're almost done reviewing everything, and that's coming out this weekend. So there's a lot that's happening. I also have my masterpiece that's coming out, but I can't talk about that right now. My masterpiece is coming out soon. Don't worry about it. Right, so we created random tensors to hold inputs and outputs. So what are tensors? Tensors are n-dimensional vectors, right? So you have one dimension, so that's just a group of numbers. You have two dimensions, it's two-dimensional, it's an Excel spreadsheet. 3 dimensions, 4 dimensions, 5, et cetera. So tensors is the generalization of the vector format for n dimensions, which is what we need, because we don't know how many dimensions our input data is going to be. And so now that we have our model, we can just build it just like this, using our input, our hidden state, and our output as the values. By the way, if you're new here, hit the subscribe button to stay up to date with my latest AI content, okay? All right, so, and tell your friends, because I'm not going anywhere. I'm going to be doing this until I will never stop. So get ready for this. We have our loss function. Our loss function, we can choose between multiple loss functions. Can anybody guess what I'm going to use? Right? We have cross entropy. We have, what's the most simple loss function that we could use here? You should know this. If you've watched at least 3 of my videos, you should know this. The answer is the mean squared error loss. Why? Because it's the most simple of them all for demo purposes. So that's what, right? We're going to find the mean squared error. We're going to find the difference between our output and our... what is PyTorch useful for? For research. For research. Not for necessarily for production, but for research. Now, what's our optimizer going to be? We all should know this. Every single person, even if you've never seen one of my videos, should know this. The answer is stochastic gradient descent, the most important algorithm in machine learning. If you don't know how gradient descent works, my friend, you need to know, because it is the most important machine learning model that you need ever in machine learning, okay? Or algorithm. Now, okay, so we've got that. I think this is supposed to be, yeah, right. Now lastly, we're going to have our training loop, and then we're good. So for 500 iterations, we're going to perform our forward pass. So y predict RMSE, Adam. I see we have some opinionated wizards in here, which I love to see. I love to see that. So that's going to be our forward pass. We're going to compute the predicted y. And once we have our prediction, what are we going to do, guys? We know how supervised learning works, right? We've done this so many times. If we don't know how supervised learning works, this is the first step. If you're new to machine learning, focus on supervised learning, which is what I'm doing right now. Once you finish supervised learning, then you move on to unsupervised learning. And what do you do when you finish? What do you do when you finish unsupervised and supervised learning? Who's got the answer for me? I'm going to wait for in the comments. Someone is going to say the answer to what you do after you learn both supervised and unsupervised learning, because I know somebody is going to know exactly what it is. Okay, so now I'm going to.
Seconds behind. So.
And okay, cool. Now, what did I call this? So in my desktop, I call this torch.py. Module attribute has no attribute. Exactly, reinforcement learning. Yes, good job, everybody. Reinforcement learning. Module has no attribute nn. Yes, okay. Let me see, what's up? Let's see here. Oh, gotcha. Torch.nn module. Let's see here. Let me see what I got here. I wonder if I do this in Colab, what the deal is. Well, actually, I need to. Let me just paste it in here. This usually goes for it. Oh, right, spaces and indentations and stuff. Right. Def forward. Oh my God. Deep learning, exactly. Let's try that out. Oh my God. See, and now you're going to watch me debug in real time, guys. Because I've got some Kaggle to do. Oh my God. This is not, okay. Guys, I'm talking about PyTorch. PyTorch examples. Not Colab. See, I was just searching that. You can see a bit of things that I was searching. I'm looking now for.
Do you want people to do Q&A?
In the meantime, just ask some questions that I'm going to answer while I get this up and running. So just we've got some great examples, by the way. I mean, look at the amount of examples PyTorch has for some of the most advanced models out there. I'm talking about variational autoencoders. My favorite supervised model, variational autoencoders. It can actually be unsupervised as well. Let's see what PyTorch has here. A 60-minute blitz. What is PyTorch? Damn, look at that. Neural networks. Right. Oh, right. Duh. That's what it was. I just needed that. Right? No module name nn. No module import torch.nn. Oh my God. Exactly, in Soviet Russia. That's what I like to hear. We've got a lot to do, guys. I wanted to give a very basic PyTorch example before stepping into the exploratory data analysis. We've got a lot packed in for this session. Seriously? What am I missing here? Let's see. Oh my God. Okay. Let's see. Seriously? See, this is that demo thing where it's like the code is working, and then right when you get to the demo, everything just kind of, I'm going to reinstall PyTorch. I mean, if that's what it's got to be, I'll reinstall PyTorch. Okay. All right.
Check the chat.
Check the chat.
The guy that added you, the torch bar. No. It's down below. The last one that referenced you. Is that?
Oh, is the torchvar object you created a struct with the reference or a NumPy array, or does it use its own vectors to create an array? It's using NumPy under the hood. I'm pretty sure it is, actually. Actually, that's what I assumed. I assumed it was using its own version of NumPy, but no, it's its own thing. ND arrays are similar, but it's not NumPy. That's very cool. Okay, what I want to do, you know what? Is check out Colab. And inside of Colab,
People are saying you should rename your .py file.
really? Oh, right. That could help. Right. Fun.py. Yeah. Nope. All right, let's see. All right, so we're going to use a new Colab. So Google Colab, check it out if you haven't, by the way. We can install PyTorch like this into Colab. Now, anybody can do this. So we just installed PyTorch, and once we install PyTorch, we're going to install, we're going to see if we can. You are seeing some real-time debugging, by the way. Let's see. On a GPU. This is definitely going to work. There we go. We are installing Pi. Let me answer some questions while we're waiting here. Rename Torch to Pi. Colab is the best, isn't it?
Do you want questions?
Yeah, questions while we're waiting for this to load.
Tech guy asked, what is Oneshot Learning? And someone else asked you to talk about the School of AI.
Okay, so what is one-shot learning? So one-shot learning is the dream. It is the dream of all machine learning to be able to learn from small data sets. And what has been done on that front? Memory augmented neural networks, MANNs. I think Facebook was probably not the first, but the most successful in marketing as a research lab. A one-shot learning algorithm. It's called the Memory Augmented Neural Network. It came out about 2 years ago, and they did it with what I think, not the MNIST data set, they did it with the Omniglot data set, which they proved that they could classify images with only I think under 50 samples. So if you want to learn more about one-shot learning, check that out. What is the School of AI next week? So that's what I have to say about that. Seriously, check this out. See guys, sometimes, in real time, you got some issues and you gotta just exactly, I think that worked. Did that work? Maybe that worked. Let's see now. So now we're gonna have some PyTorch happening. Yes, good. Good, oh my God, yes. All right, so let's see. Anyway, okay, we got to keep going, guys. We have a lot more things to code, which are not going to fail, by the way. So I wanted to give you that. This is going to work. Check that out. No GPU. Seriously, no GPUs available? Oh, we've got to activate the GPU torch.double to CPU. Oh. There's also this thing called Kaggle kernels, which I'm going to talk about as well. Okay. Let me just place this in here. Let's see now. Okay.
So you choose GPU notebook setting.
Oh, right. Notebook setting. Where's that?
runtime to GPU.
Oh, cool. There we go. Thank you. Okay, so what I'm gonna do is, I'm like determined to make this work now. Like I don't even care. I'm like, I actually have a vendetta against this because like it was totally working and now it's not. Okay, so where were we? I literally, where did I get this from? Where did I get this from? There we go. This is the deal. Now, no module named Torch. Install Torch. Yes. We installed Torch. We did that. And now, once we've installed Torch in a new code snippet, we're going to have our code run while this is installing. Answering some questions here. Change to Python 4. Perfect. Perfect advice. There's no Python 4. Okay.
You haven't defined NN. Import torch.nn as NN.
Oh, I did that. Import torch.nn as nn. I did that. That was literally like, while this is compiling, we got to keep going here. Let us do some exploratory data analysis, guys. We have our data set. Let's look at our problem, and we're going to get back to Torch. We're going to get back to Torch while this is running. So what do we have here? Let's look at our data, and then we're going to look at kernels as well. We have our data, which is going to be a set of images of different plants. We have labels for each, and I went ahead and downloaded these. And so what we can do is look at our data. So let's see if we can do this. Let's start off doing this locally, and then we're going to go further. So let's write out a read image function. Okay, so we want to read images and show them right here. So that's the first thing I'm going to do. So I'm going to say using OpenCV, and I have to import OpenCV, which is called CV2. OpenCV can be kind of a pain to install. So if you don't have this installed locally, I would recommend using either Colab or Kaggle kernels to do this in the browser. But if you do have it locally, then things can be easier for this. Okay, so that's a read image file, and I'm going to have a show image, function. Now I have a show image function. And once I do that, then I can show the image. And I'm going to have to import matplotlib for that. Import matplotlib.pyplot as PLT. And I have both of those. And this is going to be a little percentage marker that makes sure that it's in line. Okay, so now let's show some images. So let me see if that works. Invalid syntax, CVT color. Okay, good. Now let's see, sample pick equals, let's take one of our samples from our local directory, which I have, and let's just pick one. Let's say maybe like number 1, the first JPEG. Let's see if we can show this in the browser. Image is not defined. Right, so the image is going to be, no, not that. Sample pick, show image, sample pick, okay? And now we can see it. Yes, okay, so here's our first sample. And now we can kind of browse and see what we have in our data set. Right, there's a bunch of images here. Okay, let me look at some more images, right? And these images have an associated label that we're gonna now look at. Okay, so let's see how many invasive versus non-invasive images do we have, right? So let's draw a graph of that. So where are our labels? So our labels, using a pandas data frame, let me import pandas as well. Import pandas as PD. Okay, so our data frame, also let me answer some questions. What do we have here? Document clustering, LDA, latent Dirichlet allocation. Perfect method for that. It's a part of Andrew Ng's machine learning course. What is AutoML? It is Google's hyperparameter tuning framework in the browser on Google Cloud. Pillow is old, pill is better, you're right. Do you think nowadays Python is sufficient to use ML for robotics, or do we also need C++ and C? That's a great question. I mean, when it comes to robotics, you're dealing with a lot of hardware, and unfortunately, at the lowest level, when it comes to reading like these drivers and these like hardware inputs manually, a lot of those libraries are still in C, or C++. So if you're doing robotics specifically, like physical robots, not even in simulation, then I think you need some C++ knowledge to be real. Just don't think you could get through the whole thing with Python. That would be a dream. It's happening, we're not there yet. Okay, so we have our training labels, and now we want to see how much of each do we have. Right, so we need to import Seaborn. Seaborn is going to help us visualize this. It's another data visualization library. Okay. So what am I going to have the style be? Let's have it be a dark grid, and we're going to say the x-axis is going to be the invasive plants that we have, and the data is going to be our labels that we just imported into a pandas data frame. And now using matplotlib, we can give a title to this graph, just like if we had to like do a report or something on this. We'll say invasive versus non-invasive images. Yeah. Then we'll have our X label be our invasive. I guess we can specify a font size. Let's say like 20. And then our Y label is going to be, of course, the number, right? So the images versus the number, and we'll make it the same font size. I know I misspelled font size there. And okay, so let's see what that looks like. Of course, there's a okay. Right. There we go. Yes. Good. Okay. Good. So, what do we have here? Count invasive versus non-invasive. Good. So clearly we have much more invasive images where one is invasive. So that's a good thing to note. Okay, good. This is what we want. Ideally it's like half and half, so we can see like what has. And ideally we have a lot of data, but whatever. I think this is enough data, because this is an older competition, and if we look at some of the kernels, we can see that on Kaggle, we can see that it's been done. Right, so what kind of model should we build here, right? So using PyTorch, what kind of learning model should we build here to build a classifier? Now there's a lot of different convolutional nets out there. There's, AlexNet, Inception, ResNet, VGG16, VGG19. There's like a million of them. And there's not a million, there's like 10-ish, but DenseNet. What we can do is we can try them all out. But one that I have not talked about before, and I'm going to take this opportunity to talk about it, is ResNet, so residual networks. Okay, so let me talk about that really quickly, and then we'll build that. Okay, we'll build a ResNet architecture. So when we're using recurrent networks, there's a problem that occurs called the vanishing gradient problem. Now, if you want to learn more about that, just Google vanishing gradient Siraj. At least 3 videos will show up on YouTube. But TLDR, when we are backpropagating a neural network using some kind of gradient descent-based optimization strategy, like Atom, stochastic gradient descent, all sorts of gradient descent variations, the gradient gets smaller and smaller and smaller as that value is backpropagated, right? So backpropagated means, this is the value that's going to tell our weights how to update to be better at predicting the output, the real output. And so we're using calculus to optimize. Remember, neural networks are models created with linear algebra, and they are optimized with calculus. So that's where you need calculus. You need calculus to optimize, and you need linear algebra to build the models and to perform those operations on them. So the reason we use calculus is because we're computing the partial derivative of the output with respect to the weights, the partial derivative of the error with respect to the weights, and we keep doing that for every layer. So the problem is that this gradient vanishes, and this image right here shows how, you notice how it's getting more and more translucent over time. That gradient gets smaller and smaller and smaller. So to be real, so the gradient is actually a vector of the partial derivatives that are computed, right? That's the gradient. And those values get smaller and smaller and smaller, so they diminish over time. So this is a problem because the network it needs that gradient value. You can even think of the gradient as a kind of memory, right? So LSTM networks solve this for recurrent networks. But how do we do this for convolutional networks, for image-based networks? So some researchers had this, I think it was a genius idea, to literally just skip over some of the intermediary layers and by skip over, I'm talking about have the gradient skip over intermediary layers. And by doing that, it's not going to diminish. You literally just skip them over. What do I mean? Let's talk about this mathematically. So in the ResNet architecture, we have a bunch of what are called convolutional blocks. These are standard convolutional blocks, right? So convolution, pooling, activation, that's inside of a block. And you repeat that. Convolution, pooling operation, and then activation function. And repeat, 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 repeat. But what if we can add what's called an identity mapping? So what you're seeing on the left here is the novelty of ResNet, where we took f of x and we modified it by adding an extra dot product operation to it. And this is called the identity mapping. So what better way to explain the identity mapping than saying, well, first of all, we have our function f of x, and we are changing it to f of x plus x, where x is the identity mapping. And this modifies the original operation such that the gradient will not diminish over time. So in Keras, here's a very simple example programmatically of what I mean by a residual block. So in the residual network, we are renaming a convolutional block to a, by the way, don't leave, I'm going to wrap at the end, by the way. We are renaming the convolutional block to a residual block by adding in this identity mapping. So normally we would just say this right here, right? So in our block, we would say convolution, normalization, activation function, which is ReLU, in this case, which helps with the vanishing gradient problem for other reasons. There's so many little explanation tangents that could be going on here, by the way. There's so much here. But what we're doing here is we're adding this part right here. So what I have highlighted is the identity mapping. It's what is added to the initial set of operations. So notice here that the shortcut is actually, first of all, we have to specify that we want this to be a shortcut, right? So we're going to say true if we want this to be a true residual block. And if we do this, this adds this shortcut operation to it right here. And then once we've computed that, then we add it to what was initially the chain of operations, and then we return that block as a whole. So notice that it's not necessarily that something is being replaced here, it's an extra operation that's added to the existing chain of operations. But what this does is we can think about it as skipping over, because it's not a zero mapping, it's actually adding value to it, because the reason it's like skipping over is because whereas the value would diminish over time, because we're adding value to that existing chain of operations, it's a non-zero value, which is what we want. We don't want a zero value for our gradient. So that's the idea behind a residual network. The original mapping, f of x, is recast into f of x plus x. And the theory was that it's easier to optimize a residual mapping than to optimize the original unreferenced mapping. And here's the paraphrasing of what I've just said. Okay, so it is a good place to start learning AI, yes. Now, in terms of hints about what's coming up, I would say reinforcement learning, but that's all I can say right now. So EDA, we did that, ResNet. Okay, so let's do this now, right? But first of all, let's see what Kaggle has for us. So Kaggle recently released, well, they kind of renamed what already existed, but they recently released this idea of a kernel Okay, so a kernel is basically like Google Colab, but it's built into Kaggle. By the way, Google bought Kaggle, so it makes sense that they're using the same infrastructure. So if we look at a kernel here, let's see what they have here for kernels. This is the most upvoted kernel for this data set. It's saying use Keras pre-trained VGG16. So if we open up this kernel, I'll go ahead and fork the notebook. It's got literally everything I need to run this in the browser. Okay, so what this is doing is it's in the browser, it's got a notebook, it's got a Python it's got a Python interpreter in the browser. It's got all the dependencies I need for this specific data set. It's got the data set itself is imported right here that you can see as input right here with all of those, which is super handy, right? We don't have to download test.7z. We don't have to unzip test.7z. Then we don't have to combine it with the labels. It's all already there, which is super useful. Now, this is very cool, but we are not doing Keras, right? We're doing PyTorch. So let's go back and let's look for a PyTorch one if we can find one. Can anybody see a PyTorch one? Here we go, PyTorch starter 0.98. That looks pretty good. So let's click on that one and see what we got here. Fork notebook. This guy went ahead and did this in PyTorch, which is super awesome. And how are we doing on time?
We are 48 minutes in.
Cool. Wow, time flies when you're debugging. All right, so 48 minutes. Okay, we got to end this before it's too late. All right, so now what we can do is we can just run it in the browser. Notice this just compiled in the browser. NumPy, pandas, we imported that. Okay, what about Torch? Notice how I was having a problem before? Ain't no problem anymore. It is all there. I'm compiling this code, compiling. Now what is he using here, by the way? Okay, so he's transforming the data, great. He's loading up the data, cool. LR scheduler, that means learning rate scheduler. He's deciding what type of learning rate to use here based on the number of, looks like a predefined threshold of number of epochs. He's got a pre-trained weight file that so he's doing transfer learning, cool. And he's using DenseNet, okay, DenseNet, that's cool. And here's our sample submissions, submit, and train the network. Okay, cool. Well, this is gonna take a while because training neural networks is not something that just happens, right? So anyway, check that out. So that's PyTorch in the browser, everything you need preloaded with the data set. Super useful. Now, what are we going to do here? Well, we need to replace DenseNet with ResNet, and also explain what DenseNet is and how that works. But it looks like we've run out of time. Go ahead and ask some questions. I'm going to end this with a wrap, but ask some questions. VGG is, yes. But we need to understand how ResNet works, okay? Lua is awesome. Love you too. What is UNet? UNet, great idea. So UNet is interesting because it's kind of a reflection of itself in the later layers. We'll talk about that. Pooling is a great example. Pooling is, not all of the data in the input is relevant to the output. So what pooling does is it chooses what's the most relevant. So what does most mean? Well, most in the case of max pooling can be what has the most, what's just the biggest number in some region of the input, and then we do that. So that's max pooling, and that's generally the most used pooling operation in neural networks. There are other kinds as well. Can you talk about learning rate scheduler API? For PyTorch, I'll talk more about PyTorch. Where can we learn more about PyTorch? Guys, so what I do when I'm learning about any kind of code is I don't look at anything but GitHub, right? I just go straight to GitHub and I look at some example code, and hopefully the example code is well documented. This is the repository to look at. Reinforcement learning is probably what I look at because that's what I'm most interested in right now. This is cool. Okay, I mean, it could have better documentation, but that works. Now I'm going to end this with a wrap, and I'm going to just pick some random word from the comments. Let me see here for.
Alphabet acrobatics rap by Blackalicious.
Okay.
2 people have said that.
Alphabet acrobatics.
Or alphabet aerobics as well.
Okay. Alphabet aerobics. Okay. Cool. I found it. Never heard this before.
Now it's time for our wrap-up. Let's give it everything we
Are you serious, guys? You guys are trolling me, aren't you? All right, let's do this. I'm waiting for the beat, seriously. Is this even a rap? Like, okay, fine. All right, rap on Elon Musk or Golang. I like Golang. I do it. No, let me restart. I like Golang. No. See, hold on. This is just the most whack beat I've ever heard. Like, how is anybody supposed to rap over this? It's getting faster as well. There's not even like a set tempo here. It's just, I'm gonna just do it anyway. Here we go. I like Golang. I'm slow, man. I like do it like I'm Elon Musk, man. It's going faster and faster. I like concurrently. See, I keep my Go routines running. You see, yeah, Go routines. This is so whack, dude. This is seriously like, I'm just gonna acapella this. I like Golang. It's got concurrent subroutines. That's how it goes. You see what I mean? I do 1, 2, 3. It's distributed. Can't you see? I do it across different TPUs and GPUs. I do it on my CPU. I do it on my... All right, that's it for this live stream, guys. That is how we do it. We literally don't care if we succeed, if we fail, if we do both, because we just keep on going no matter what. Nothing will stop us. We are going to do so much good for the world. And thank you for tuning in. For now, I've got to make some videos. So thanks for watching.